Friends, welcome to the lecture number 8. In this lecture, we are going to discuss the second part of the application of the equilibrium constant. In the first part, in the lecture number 7, we have already discussed about the two applications of the equilibrium constant. That is the extent of reaction, how we can able to predict the extent of reaction and how we can able to predict the direction of the reactions. In this lecture, we are going to discuss the determination In this lecture that we are going to discuss the determination of the concentration of equilibrium mixture. Suppose you have been given the initial quantity of the reactants and you want to know what will be the concentration of the reactant and product at the time of equilibrium. That you can do if you know the relationship between the equilibrium constant and the molar concentration of the reactant and product at the time of equilibrium. So we are taking one very simple example to understand the relationship between the Kp relationship between the Kc and Kp with the amount of substance the relationship between the Kc and Kp with the amount of substance that is reacted. For that, we have taken the example. We have taken the 1 mole of nitrogen gas and 3 mole of hydrogen gas in a container, in a vessel which is closed, and it has been kept there for some time until it has reached to the equilibrium. So the balance equation for this reaction will be this. This is the reaction. In this reaction, you will find this is nitrogen gas we have taken, hydrogen gas we have taken, and along with this, the product is ammonia. We have taken 1 mole of nitrogen, 3 mole of hydrogen initially, and after some time, let assume at equilibrium X mole is reacted, X mole of nitrogen reacted, and this X mole will produce the 2x mole of the ammonia. So we can write at the time of equilibrium, 1 minus x, 3 minus 3x and 2x. 2x, that is the concentration as the equilibrium. So at the concentration, at the equilibrium, the concentration of nitrogen is 1 minus x, hydrogen 3 minus 3x and nitrogen 2x. Why it is 3x? Because you can see 1 mole of nitrogen produced will react with the 3 mole of hydrogen and it will produce 2 mole of nitrogen. So this will at the equilibrium, and we have taken the vessel, we have taken the volume of the vessel is 1 liter. So naturally this will be, you can say, mole per liter. So we now calculate the Kc, that will be given by this concentration of NH3 divided by concentration of nitrogen and concentration of hydrogen. We will put this value. So what we get? 2x whole cube divided by N2 is having 1 minus x, and this will be 3 minus 3x. This is the relationship we can find. This is in terms of Kc. Now we want to know what will be the Kp. Kp means we have moved. Kp will be from this equation, we can easily formulate this partial pressure of NH3 divided by partial pressure of N2 and partial pressure of hydrogen. So we want this information about the partial pressure. How do we able to calculate the partial pressure? And for this we have to make the total moles. We have to know the total moles. Total moles you can calculate, that you already know, 1 minus x plus 3 minus x plus 2x, that will be total mole, and it will be comes around 4 minus 2x, that will be the total mole. And we know partial pressure is basically, what is partial pressure? Partial pressure is basically the mole fraction and the total pressure in the vessel, because this is a gaseous mixing, and in this gaseous mixing, gaseous reactions, you will find that there will be a specific amount of pressure will be created by these three gases when they are in equilibrium. Suppose this total pressure is P, capital P. So we can say the partial pressure of NH3 is equal to is mole fraction. What is the mole fraction? Total mole, and there the mole at the equilibrium, that is 1 minus x divided by 4 minus 2x into total pressure. Total pressure, suppose P. Okay. Partial pressure of H2 we can calculate, that is mole fraction of H2. What is the mole? That is mole of hydrogen 3 minus 3x by total mole 4 minus 2x into pressure P. And for the P into, you can usually calculate, that is 1 minus x divided 4 minus 2x into P. So when we put this value in this formula, this is partial pressure of ammonia, partial pressure of hydrogen, partial pressure of nitrogen. And when we put this here, you will get the Kp in terms of substance consumed. Okay, this is a very important relationship that you need to understand. Now what we will do to understand it, which type of question will come, numerical will come, that we will solve it, and you can able to have the much more clear idea. This is one numerical. This type of numerical may come in your exam. Ammonium carbonate is a solid. When it is decomposes and it will produce this ammonia gas and carbon dioxide gas, and it will be in the equilibrium at a particular temperature, and at that temperature the equilibrium pressure is found 3 atmosphere. You have to calculate the Kp for this reaction. So for that, what we have to do, we have to, that this is a solid and this is gas. Naturally, these are heterogeneous equilibrium. In this case, the pressure is created by the gas, not by the solid. So we have to first assume, let the pressure of carbon dioxide, CO2 gas at equilibrium is P. If it is P, then ammonia NH3 have the pressure will be partial pressure of NH3. What will be this? It will be 2P. Why it is 2P? Because we know the pressure is directly related to the number of moles. Because it is a equilibrium condition, here temperature is constant, volume is constant, because we are making the experiment in a closed chamber. So at that time we can correlate with the pressure and with the moles. Now it is a twice more than this, double mole than this carbon dioxide. Naturally, if it has the pressure P, then pressure of the NH3 gas, partial pressure of the NH3 gas will be 2P. So total pressure it is given P plus 2P is equal to 3 atmosphere. That is given here. The 3 atmosphere for the above reaction. If the equilibrium pressure is 3 atmosphere, so you can write the 3. So P is coming around 1. So partial pressure, now we understand partial pressure of from this calculation. Now we can say partial pressure of your carbon dioxide is 1, and partial pressure of ammonia, it is, what is this? This is 2. Right? So what is Kp here? Kp, you partial pressure of ammonia per whole square into partial pressure of CO2. Okay? Because in the heterogeneous equilibrium we will not consider the solid part, because the solid part have a constant moles, constant concentration, right? So Kp will be this, and this will be whole square into 1, that will be 4. So the answer will be the E. Okay, this type of question will come and you have to solve this way. Now we are going to the next problem. This is another very important, very interesting question. Equivalent amount of hydrogen and iodine taken are heated in a closed vessel till the equilibrium is obtained. If the 80% of hydrogen is converted to Hi, the equilibrium constant at Kc at the temperature will be, option is given 2, 6, 64 and 20. So this type of when question comes, then you have to have the balance equation first. This is the balance equation, right? This equation shows that 1 mole of hydrogen will reacted with the 1 mole of iodine, and it will produce 2 mole of Hi. So suppose you take 1 mole of hydrogen and 1 mole of iodine. initially. After that, it is given 80% of hydrogen is converted to HI. Means 80% means what? Now 0.8 moles has been reacted with the 0.8 moles of iodine, and it will going to give you the 1.6 moles of this. So 80% means here the remaining at the equilibrium time, at equilibrium you will find that 1 minus 0.8, 80%. This is 1 minus 0.8. This is 0.8 into 2. Means 1.6 mole is produced. So it is at the equilibrium 2 moles of hydrogen, 2 moles, 0.2 moles of hydrogen and 0.2 moles of iodine, and it will produce the 1.6 mole of hydrogen iodide. So this is the things, this is the concentration at the equilibrium time. So its equilibrium constant will be 1.6 whole square divided by 0.2 into 0.2, and it will be coming around 64. So this will be the right answer. In a reaction, this is the reaction, 2 moles of A, 3 moles of B and 2 moles of C are placed in a 2 liter flask, and equilibrium concentration of C equilibrium concentration of C is 0.5 mole per liter. We have to calculate the equilibrium constant. You have to calculate. For that, this is the relationship, this is the reaction. At the initially we have taken 2 moles of A, 3 moles of B and 2 moles of C and 2 liter flask. So this is having mole per liter is 1, this will be mole per liter is 1.5, and this will be mole per liter 1. At equilibrium what is happened, that its concentration is 0.5. If its concentration is 0.5, then what will be the concentration of these two things that we have to calculate, we have to understand. See here, 2 moles when dissociate, it will give the 2 moles of B. So 0.5 mole has been dissociated because 1 mole was the initial concentration. So this 0.5 mole will produce 0.5 mole of B. So we can write at the equilibrium time it increases 2. Now 2 moles will produce 1 mole of A. Then 1 mole of C produce half mole of this. So this will, there will be addition will be 1.25. So at equilibrium the concentration will be this. So now easy for you to calculate the Kc. Kc is given by, that is C is there given by 0.5 the whole square divided by your A is 1.25 and your B is 2 the whole square, and if you calculate it will be coming around 0.05. C will be the right answer. Okay, in this way the numerators will come and you have to solve it. That is all for today's lecture. In this lecture we have discussed about how we can able to calculate the concentration at the equilibrium point, and there is another thing that we will discuss in the next video, that is when there is a degree of dissociation is given, at that time how do you calculate the concentration at the equilibrium point. That we will discuss in the next video. Okay, thank you very much for watching this video. I think that will be beneficial and helpful to you. If you like this video, you can share this to your friends. Thank you very much for watching. Thank you.